Okay, we're going to talk about section 7.2, the rest of it here. It is U-substitution in definite integrals. Let's go ahead and get started. So we've talked about the difference between indefinite integrals and definite integrals. We've talked about U-substitution in indefinite integrals. Now we need to add in what happens if you have a definite integral that you want to solve, maybe something like this, the integral from 0 to 4 of x minus 4 squared dx. And you want to solve that in terms of, you want to solve that, and U-substitution is the way that you want to go about it. Now, this is a problem where you could probably figure out what the antiderivative was without using U-substitution, but let's use U-substitution in a simple example, and then we'll progress to things where it's harder and harder to do the problem without a U-substitution. So there's really only one piece of this function that looks like it's kind of an inside part, and that is the x minus 4. So we're going to let that be our u. So u equals x minus 4. I don't like that. Let's try this. U equals x minus 4. All right. We are going to take and find du. Du will be pretty straightforward. It's just dx. All right. And so we're going to make the substitution. So I'm going to leave the bounds off for now. Now, I mentioned this before in class, I think. The U substitution is just to help us simplify the integral. Okay, so if and sometimes it works pretty well. So if I make the substitution here, I'll have u squared and I'll have du. And I've made a big deal about how the differential and the independent variable have to match. Also, these bounds were set up for a function in terms of x, and hopefully in the exploration you saw the relationship between x and u and why the bounds can't be the same. But the fact of the matter is that the bounds in terms of x are not going to be the same as the bounds when we've changed this function to u. All right, so to figure out what those bounds are, we have to change them. Okay, so what we'll do is we'll take this function u, or this equation in terms of u and x, and this will be sort of the key to switching our bounds from x to u. So I'm going to go find u of 4. U of 4 is equal to 4 minus 4, which is 0. Okay, so I'll put 0 up here. And then I'm going to go find u of 0, because I'm putting in the lower bound now. So u of 0 is equal to 0 minus 4, which is equal to negative 4. Right, so that's my new bounds. And if I do that, then I can just antiderive and evaluate from the lower or the upper bound to the lower bound, just like I would with any definite integral. So I add 1 to the power and divide by it, so I get 1/3 u cubed, or just u cubed over 3. Evaluate it from negative 4 to 0, and then I'm going to put in negative 4 to the 3rd power over 3 minus, sorry, that should be 0. Good job, Cresswell. 0 to the 3rd power, which will just be 0, minus negative 4 to the 3rd power over 3. And so this ends up being just a negative of negative 64 over 3. And there we go. So there's our final answer. All right. So let's do another one. Let's go on to go on to a different example. Let's bring in some trig functions here. So let's do the integral from 0 to pi over 3. And we've got tangent of x times secant squared of x dx. Now, it turns out on this one you've actually got some options for what to pick for u, but I'm just going to pick the one that I think is the clearest. And that is to pick tangent as u, because the derivative of tangent is secant squared. All right, so I'll pick u as tangent of x. And then when I derive this, I'll get du is equal to secant squared x dx. I can take that piece here and plug that in for or as du. Tangent will be u. And then I'm going to leave my bounds for now. So this will end up being just u du. Right? And then I'm going to go over here and do a little bit of scratch work and find what is u of pi over 3. Well, u of pi over 3 would be tangent of pi over 3. Tangent of pi over 3 turns out to be, where did I write it down? The square root of 3. And then let's find u of 0. U of 0 would be tangent of 0 equals 0. You could figure out that this was root 3 from the special right triangles. Pi over 3 is 60 degrees. So you could look at the 30, 60, 90 right triangle to figure that out. Okay, so our lower bound is going to be 0. Our upper bound is going to be square root of 3. And then we're going to evaluate this, the integral here, right? So we're going to take the antiderivative. So that would be 1/2 u squared evaluated from 0 to square root of 3. And then we can plug in the upper bound minus the lower bound. So this would be 1/2 square root of 3 squared minus 1/2 u squared. And so that ends up being just square root of 3 squared is 3, so 3 over 2. Okay, so that there's another type of definite integral there. Let's look at one where we need to use a trig identity to solve it. So the next one, I should just get this over and go to this page here. So this example is going to be the integral from pi over 2 to 2 pi. And we're going to take and try to figure out how to antiderive cosine cubed of x dx. All right, now this one we're going to have to do a little bit of work before we get down to the answer. So cosine cubed doesn't have an obvious u. If you pick cosine, you'll end up with the derivative or du of being sine. You can see there's no sign that shows up here. Okay, so we're going to use a trig identity to finish this one out. And the identity that we're going to use is this one, that sine squared x plus cosine squared x equals 1, or cosine squared theta plus cosine squared theta equals 1. All right. So in place of cosine squared, in fact, I'm going to write this out explicitly. So we're going to change this. So this will be pi over 2 to 2 pi. We're not changing anything fundamentally in the integrand yet. This will be cosine squared times cosine x dx. All right, so then in place of cosine squared, I'm going to put 1 minus sine squared. In other words, I'm going to move this sine squared over to the other side of this equation. It's still an identity. And then I'm going to replace that with, or I'm going to put that in for cosine squared. So I get this. Integral of pi over 2 to 2 pi of 1 minus sine squared times cosine squared. Oh, sorry, times cosine of x dx. And now I have a little bit more flexibility with what I pick as my u. Again, guess and check will work eventually, right? But you can also kind of look at this and think, all right, well, if I pick cosine, I'm going to get a sine dx. There's not a sine dx, there's a sine squared, but that's not the same, obviously. If I pick sine squared, that's not going to work because I'm going to have to do the chain rule. If I pick sine, that might actually work, because if I think ahead here, if I do sine, then I would have 1 minus u squared, and the derivative of sine is cosine x dx. So let's try that. All right, so let's go off to the side, and we'll try to make this as clear as we can. So we'll let u be sine. All right, and then we will let, so if we do that, then du will be equal to cosine x dx. And so we'll make the substitution, and then we'll come back and get the bounds here in a second. So this will be 1 minus u squared. And then du is cosine x dx, so that's going to just replace all of that. So that would be du. And then we'll go get the bounds. So the bounds will go, so we need to figure out what u of 2 pi is. So u of 2 pi. U of 2 pi would be sine of 2 pi. That turns out to be 0. And then we need u of pi over 2. That's sine of pi over 2. That turns out to be 1. So our bounds then are going to be from 1 to 0. And this has the problem of getting the bounds out of whack. So you've got from 0 is smaller than 1. It's in the upper bound. So we need to change that. So this will be from 0 to 1, the negative of the entire integral of 1 minus u squared du. And now we can antiderive and evaluate. So I end up with, so I'll just leave this negative out in front of everything. So I've got negative u minus, it'd be u cubed over 3. And that's going to be evaluated from 0 to 1. When you do the math, so when you compute this out, then what you end up with is, I don't think I need to fill in all of the work, but you end up with negative 2/3. Okay. Now, I try to say this every year I teach this. There is a way to solve this that makes a mistake that ultimately corrects itself. And so one thing that you can do is, if you hate, or no, I'm not going to say you can do it. One thing that sometimes students do is they will forget to make this changing of the bounds here with it in terms of u. And then, so they'll leave everything in terms of, they'll make the u-substitution, but they'll leave the bounds. So in this one, for example, it would be, you'd be here with bounds that are in terms of x, so it would be pi over 2 to 2 pi. They will keep going, then they will antiderive here, and then they'll replace the u with sine of x, with the function in terms of x, leaving the bounds still in terms of x. You end up with the same answer, it turns out, but you've got a couple mistakes. So one mistake is here, when you don't change the bounds, you actually have bounds that are nonsensical in relationship to your original problem and the integrand. And then you have a mistake that you're evaluating these bounds, but you never actually do the evaluation of the bounds in terms of x, because then you plug the x back in, the expression in terms of x. And so you have a few lines of logic here that actually don't make sense. So you will end up with the same answer, but you're going at it in a way that is technically nonsensical on your path to the final answer. All right, and so that's it for u-substitution in the context of definite integrals.